Long before the telescope, ancient astronomers tracked the cosmos with stunning precision. This video uncovers how ancient astronomers built precise observatories without telescopes, revealing feats of engineering and intellect that challenge our modern assumptions. By the end, you will understand the forgotten methods that let our ancestors map the heavens using only stone, shadow, and the naked eye. How did they move multi-ton stones into perfect alignment with distant stars? And why did they encode celestial secrets into their most sacred structures? What does their enduring legacy say about our own place under the stars? The night sky was their constant companion, a vast celestial clockwork they learned to read with astonishing skill. Ancient astronomers began with the most fundamental task of all, watching the same sky night after night, year after year. They noticed how certain stars returned to the same position with unwavering regularity, how planets moved against the backdrop of fixed lights, and how the moon cycled through its phases. This was not casual stargazing, it was a disciplined, generations-long project of data collection. They were building a mental model of the universe, one observation at a time. From this deep familiarity, they could predict the future. They knew when the sun would reach its lowest point in the winter sky, signaling the return of longer days. They could anticipate the moment the moon would slide into the Earth's shadow, creating a lunar eclipse. This predictive power was absolutely critical. It allowed them to create accurate calendars that told farmers when to plant and when to harvest, and it informed religious ceremonies tied to specific celestial events. But how do you translate this knowledge of the sky into something permanent, something you can build upon? The answer lies in the tools they engineered from the landscape itself, turning simple observation into monumental architecture. Their most essential tool was nothing more than a simple stick planted firmly in the ground. This was the gnomon, the heart of the earliest sundial. By watching the shadow it cast move and change length throughout the day, an observer could track the sun's journey across the sky with remarkable clarity. But their toolkit extended far beyond this. For perfect vertical alignments, they used a plumb bob, a weighted string that always points straight down, providing a true reference line to the Earth. For measuring time at night when the sun was gone, they relied on water clocks. These devices, known as clepsydras, used the steady drip of water from one container to another to mark the passing hours, allowing them to time the rise of a star or the duration of an eclipse with surprising accuracy. Another instrument, the merkhet, was a sighting tool made from a palm rib with a slit cut in it. An astronomer would hold it up, peering through the slit to line up a specific star with a plumb bob hanging beside it. This simple act created a perfect celestial meridian, an imaginary north-south line in the sky. What is truly astounding is not the complexity of these instruments, but their profound simplicity. They were built from everyday materials: stone, wood, water, and string. Yet through meticulous craftsmanship and endless repetition, they were calibrated to a degree of precision that feels almost impossible to us today. This was an era where knowledge was not stored in books or computers, but in the careful shaping of a tool and the practiced hand of its user. Their ingenuity proves that the most advanced technology is not always about having the most powerful tools, but about having the deepest understanding of how to use them. This profound understanding of basic principles is what allowed them to take the next great leap, moving from handheld instruments to building colossal observatories directly into the Earth itself. Stonehenge rises from the English landscape not as a random circle of stones, but as a colossal machine built of rock and sky. Its builders understood something profound, that the sun and moon are predictable, and they engineered their monument to capture these celestial moments with breathtaking accuracy. Long before the first massive sarsen stone was erected, the process began with simple post holes dug into the chalky earth. These were not foundations, but precise markers used to plot the exact points on the horizon where the sun would rise and set at the solstices. Through years, perhaps generations, of patient observation, they recorded the sun's most extreme northern and southern positions, effectively drawing a giant celestial calendar on the land itself. The most famous of these alignments involves the heel stone. On the summer solstice, as viewed from the center of the circle, the sun appears to rise directly over this solitary pillar, framing the dawn in a blaze of stone and light. Achieving this was no accident. It required an intimate knowledge of the landscape and a masterful application of basic geometry to transfer those precise astronomical sightlines into the permanent placement of multi-ton stones. This was more than a temple. It was a sophisticated observatory that tracked the seasons, predicted lunar cycles, and cemented a connection between the earthly and the divine. The sheer scale of Stonehenge reveals a society that had moved beyond simple stargazing to a deep understanding of celestial mechanics, encoding that knowledge into an architecture meant to last for millennia. But this story of turning the sky to stone was not unique to the British Isles. Across the globe, other cultures were performing their own remarkable feats of cosmic engineering. This silent language of numbers and shapes was the invisible blueprint for every stone they set into the earth. Ancient astronomers possessed a deep, intuitive grasp of geometry, a practical mathematics that allowed them to translate the sweeping arcs of the sky into precise architectural plans. They understood the properties of triangles and circles long before these principles were given formal names like the Pythagorean theorem. To align a doorway with the rising point of a specific star, they were effectively solving a complex geometric problem. They had to calculate the correct angle from their viewing position to a point on the distant horizon, a task that required an understanding of right-angled triangles and the relationships between their sides. A simple rope could become their most powerful calculating tool. By knotting it in specific ratios, they could create a perfect 3-4-5 triangle, guaranteeing a perfect right angle for their foundations. They also mastered the circle, dividing its 360 degrees into manageable arcs to track the sun's yearly journey. At Newgrange in Ireland, a tunnel perfectly aligned with the winter solstice sunrise was not stumbled upon by chance. It was the result of meticulous calculations of the sun's altitude and azimuth, its position relative to the horizon on the shortest day of the year. The builders used this mathematical foresight to design a structure where, for just a few minutes each year, a narrow beam of sunlight would pierce the darkness of the inner chamber. These were not crude estimations, but refined applications of mathematical principles that ensured their observatories would capture celestial events with pinpoint accuracy, year after year, century after century. Their calculations were simple in their components, yet profoundly effective in their application, creating a legacy of stone that was as much a product of the mind as of muscle. But even the most brilliant mathematical plan had to be adapted to the real world, a world of shifting terrain and specific local conditions. The land itself became their greatest ally in this cosmic quest. Across the ancient world, astronomers did not simply clear a flat plain and start building. They sought out locations where nature had already done half the work. They looked for hills that perfectly framed the rising sun on the equinox, valleys that channeled the moonlight on a specific night, and unique rock formations that served as permanent, unmovable markers on the horizon. By harnessing these natural features, they created observatories of immense scale and precision without needing to move mountains of their own. A stunning example of this principle survives in the coastal desert of Peru. At Chanquillo, 13 towers stand in a row along a barren ridge. From a specific observing point to the west, these towers do not point at the sun. They act as a giant stone calendar against its path. Throughout the year, the sun rises at a different point along this jagged skyline. On the summer solstice, it appears over the first tower. On the winter solstice, it rises over the last. Every day, its position shifts, marking the passage of time with a reliability that no human-made mechanism could match. This was a solar calendar built directly into the Earth's own contours. The builders of Chanquillo understood the sun's trajectory so perfectly that they used the natural ridge to amplify its motion, turning a simple line of towers into a precise astronomical instrument. This symbiotic relationship with the landscape was a stroke of genius. It minimized the immense labor of construction while maximizing the accuracy of the observations. It reveals a philosophy where humanity did not seek to conquer nature, but to collaborate with it, to listen to its rhythms and build in harmony with its design. These structures were not just placed on the land, they were woven into its very fabric, making the celestial dance a permanent and visible part of the human world. But why go to such extraordinary lengths? What powerful force drove entire cultures to invest generations of labor into aligning stone with star? These stone giants were far more than cold instruments of measurement. They pulsed with a profound cultural and spiritual life, serving as bridges between the earthly realm and the cosmos above. For ancient societies, the movements of the sun, moon, and stars were not merely mechanical cycles. They were the visible actions of gods and ancestors. A lunar eclipse might signal a deity's displeasure, while the solstice sun's return promised renewal and favor. This deep spiritual connection transformed their observatories into sacred spaces where science and religion were inseparable. The precise tracking of Venus was not just an astronomical exercise, it was a way to divine the will of a powerful celestial god. The knowledge of when to plant crops, derived from the sun's position, was a sacred duty, ensuring the survival of the community by aligning human activity with the divine order. This powerful motivation, the need to please the gods and ensure cosmic harmony, is what drove entire cultures to dedicate generations of labor and immense resources to these monumental projects. We see this beautiful fusion clearly at the Mayan Caracol Observatory. Its unique spiral structure, resembling a modern telescope dome, was precisely aligned with the extreme rising and setting points of Venus. The Maya saw Venus as a war god, and its cycles dictated the timing of military campaigns and royal coronations. The observations made from this tower directly shaped the political and spiritual fate of their civilization. The accuracy of their celestial predictions lent rulers an air of divine authority, proving they could communicate with the heavens. This blend of practical need and deep faith created an unstoppable engine for innovation. It was this sacred imperative that justified the immense effort, turning a scientific pursuit into a communal act of worship and survival. The knowledge gained from these sacred sites was far too valuable to be lost with a single generation. Their knowledge was a living library, carried not on parchment but in the minds of the people. In societies without extensive written records, the precise movements of the stars were preserved through an unbroken chain of oral tradition. Elders and specialized priests committed vast astronomical data to memory, reciting complex cycles of the moon, the wanderings of planets, and the exact dates of solstices through songs, chants, and epic stories. A single melody could encode the entire 18-year cycle of the moon, its rhythm mirroring the celestial rhythm it described. This was not a casual hobby, it was a sacred duty. The person who held this knowledge held the key to the community's survival, knowing when to plant, when to harvest, and when to perform the ceremonies that kept the world in balance. This system of memory fostered an incredible social cohesion, as everyone relied on these chosen individuals and participated in the rituals that reinforced this celestial calendar. The proof of its staggering accuracy is written in stone. Structures like Stonehenge and the towers of Chankillo remained functional for centuries, their alignment still true long after the original builders were gone. This was only possible because generation after generation precisely maintained the knowledge of how to use them, passing down the exact sightlines and meanings through an unshakable oral tradition. This cultural continuity was the lifeblood of their science, ensuring that an observation made 1,000 years prior was still as relevant and actionable as it was on the day it was first sung into memory. Across the globe, this universal human drive to understand the sky led to a fascinating diversity of methods, as each civilization looked upward and developed its own unique way of reading the cosmic clock. While the stones of Europe and the Americas charted the sun, another great astronomical tradition was unfolding along the fertile banks of the Nile. Here, the rhythm of life was dictated by the sun's annual flood, and Egyptian astronomers became masters of solar observation. Their most iconic instruments were the towering obelisks, whose sharp tips cast long, clean shadows that swept across precisely marked temple courtyards. By tracking these shadows, priests could pinpoint the solstices and equinoxes with incredible accuracy. They also designed long, dark temple corridors aligned so that on specific days, like the king's coronation anniversary, a beam of sunlight would travel the entire length of the hall to illuminate a statue of a god seated in the inner sanctum. This was astronomy in service of the state and the divine, creating a calendar that synchronized the agricultural cycle of planting and harvest with the celestial certainty of the sun. Far to the east, in the land between the Tigris and Euphrates rivers, Mesopotamian sky watchers looked up with a different focus. Their flat, open plains were ideal for observing the entire night sky, and they became consumed with the complex motions of the moon and planets. Their signature structures were not sun-aligned corridors, but the massive ziggurats, stepped pyramids that served as artificial mountains reaching toward the heavens. Priests would climb to the highest platforms to spend the night charting the wanderings of Mars or the phases of the moon. This relentless, data-driven observation over centuries allowed them to predict lunar eclipses and even calculate the recurring cycles of Venus. Where Egypt sought order and regularity in the sun for its agricultural society, Mesopotamia sought patterns in the chaotic movements of planets, believing they held messages about the fate of kings and empires. This fascinating divergence proves there was no single path to precision. One culture built low, long structures to capture a single shaft of sunlight, while another built towering platforms to embrace the entire night sky. Yet both, through methods perfectly tailored to their environment and beliefs, achieved a stunning mastery of celestial mechanics. They demonstrate that human ingenuity is not a monolithic force, but an adaptable one, capable of finding multiple solutions to the same fundamental challenge of understanding the cosmos. But this knowledge of the stars was not confined to marking sacred days or reading omens. It was also the key to unlocking the world itself, guiding travelers across trackless seas and through the featureless desert. The stars were a compass painted on the dome of the night. For an ancient sailor far from land, with only the waves and the wind for company, the steady position of Polaris, the North Star, was a lifeline. By measuring its angle above the horizon with a simple device like a camel, a wooden card on a string, a navigator could determine their latitude, knowing exactly how far north or south they had traveled. Constellations served as seasonal signposts. their appearance and disappearance marking the safe windows for long voyages across the Mediterranean, the Indian Ocean, and the Pacific. This was not theoretical knowledge, it was a matter of survival. The success of trade, the discovery of new lands, and the very lives of the crew depended on the ability to read the celestial map. On land, the same imperative drove the creation of observatories along these critical trade routes. The Nabateans, masters of the incense trade, built high places like the altar at Jabal Rum in Jordan, where the rising of specific stars signaled the start and end of caravan seasons, synchronizing the movement of goods across the desert. For the farmer tied to the soil, the sky was an immense, unerring calendar. The first appearance of the star cluster known as the Pleiades just before dawn might signal the time to sow seeds, while the sun's alignment with a specific standing stone told the community it was time to harvest. These were not vague estimations, they were precise, actionable dates encoded into the landscape. A stone circle was more than a ritual site. It was an agricultural bulletin board carved in granite, its alignments broadcasting critical information to everyone in the community. The survival of the entire society, the difference between a bountiful harvest and famine, hinged on this celestial timekeeping. This deep integration of astronomy into the most fundamental aspects of life, from commerce to agriculture, created a powerful, self-perpetuating cycle. The need for accurate navigation and reliable calendars demanded ever more precise observatories, and the data from those observatories, in turn, made navigation and farming more successful. This practical necessity was the engine that drove the science forward for millennia. Yet with so much depending on their accuracy, how did these ancient astronomers guard against error? How could they be sure that the star rising over a distant mountain peak was truly in the same place it had been for their ancestors? The answer lies in a culture of relentless verification and a simple, powerful technique that any modern scientist would recognize: redundancy. They did not rely on a single observation or a lone individual. Instead, they built in multiple layers of cross-checking. An alignment for the winter solstice sunrise might be verified not just by one stone, but by a pair of stones that framed the sun's disk, and further confirmed by a shadow cast from a separate pillar. They repeated their observations over many years, noting any tiny discrepancies and adjusting their markers accordingly. Generations of priests would use the same sightlines, passing down notes on any shifts, understanding that the human eye is fallible and that atmospheric conditions can play tricks. This long-term, communal approach to data collection effectively averaged out the small, daily errors, revealing the clear, unwavering signal of the celestial cycle beneath the noise. Their greatest tool for precision, therefore, was not a single instrument, but the accumulated patience of centuries. This meticulous process of verification was built on a foundation of collective effort. No single person's observation was ever taken as absolute truth. Instead, multiple observers would independently track the same celestial event, and their findings would be compared. If one person noted that a star rose just to the left of a certain mountain peak, while another saw it slightly to the right, they would average these positions to find the most probable true alignment. This simple act of averaging out human error is a cornerstone of modern science, yet it was practiced with profound effectiveness thousands of years ago. They understood that the eye could be deceived by haze or fatigue, so they trusted in the power of the group to see more clearly than any individual. This principle was then etched permanently into their architecture. A single important star might be targeted by 2 or even 3 separate stone alignments within the same structure. If one sightline was obscured by weather or a shifting stone, the others would still provide the necessary data. The Bighorn Medicine Wheel in Wyoming is a masterclass in this redundant design. Its 28 spokes radiating from a central cairn are not merely decorative. Specific spokes point precisely to the rising points of the sun at the summer solstice, but also to the bright stars Sirius, Aldebaran, and Rigel. This created a network of celestial checkpoints. If clouds hid one star, another would be visible, ensuring the calendar never failed and the ceremony was always performed at the correct moment. This was more than backup. It was a resilient system designed to withstand the uncertainties of the real world. Their entire methodology was a form of ancient quality control, a proactive search for consistency across generations. But these verified observations were useless if they could not be preserved and refined for the future. How did they document a star's position not just for next year, but for 100 years from now? The answer lies not on fragile parchment, but in the deliberate and incremental adjustment of the stones themselves. Each generation of watchers would build upon the records of the last, sometimes making tiny, deliberate shifts to the placement of a marker stone after noting a consistent discrepancy over many years. This slow, careful refinement turned their observatories into living documents, their alignments honed to a finer and finer edge by the accumulated wisdom of centuries. The structure itself became its own permanent and perfect record. Their long-term data collection was a generational relay race, with each age passing the baton of celestial knowledge forward. In ancient China, court astronomers maintained meticulous records of every eclipse, comet, and planetary conjunction for over 1,000 years. These were not isolated notes, but a continuous, unbroken logbook of the sky. By comparing records from one century to the next, they could detect subtle patterns invisible to any single observer. They noticed, for instance, that lunar eclipses recur in a cycle of approximately 18 years. This cumulative knowledge, refined over generations, allowed them to predict future celestial events with breathtaking accuracy. Their predictions were not guesses. They were the product of data analysis on a scale that is difficult for us to comprehend. This same principle of long-term refinement was applied directly to their observatories. A stone alignment that was 99% accurate for a grandfather might be adjusted by his grandson, who had recorded a tiny, consistent error over his own lifetime. The structure itself was never truly finished. It was a living instrument constantly being honed and perfected. The patience this required is almost beyond our modern imagination. An astronomer might spend his entire life making only a single, minor correction to a celestial calendar, a correction whose full value would not be realized until his great-grandchildren were born. This was a science built not on quick results, but on profound faith in the future, a belief that knowledge was a gift to be passed down and polished by those yet to come. This slow, deliberate accumulation of precision over centuries laid the groundwork for the next great challenge, transforming these refined astronomical plans into colossal structures of stone. The sheer scale of these projects demanded engineering on a heroic level. Moving a multi-ton sarsen stone from a quarry 20 miles away was not a matter of brute force alone. It was a symphony of applied physics and meticulous organization. They mastered the use of simple machines, turning impossible tasks into manageable steps. To transport a colossal stone, they likely laid a track of smoothed wooden rollers, constantly moving the rearmost log to the front in a continuous, painstaking procession. Greased with animal fat, these rollers reduced friction just enough to allow teams of people, pulling on ropes made of plant fiber or leather, to coax the stone forward inch by inch. Once at the site, the even greater challenge began, raising the stone. Here, levers and frames made of massive timbers came into play. Workers would slowly pry one end of the stone upward, while others stacked wooden cribbing beneath it. Lift an inch, stack a block. Lift another inch, stack another. This gradual process, repeated over days or weeks, would eventually walk the stone into a vertical position. For the immense lintels that cap the structure at Stonehenge, they likely constructed great earthen ramps, dragging the stones up the slope and then lowering them precisely onto their supports. But moving the stone was only half the battle. The true test was placement. To ensure a lintel was perfectly level, they used water. A simple trough carved into the stone and filled with water creates an unerring horizontal line, a liquid level that defies the uneven ground beneath. For vertical alignments, a sighting tube, perhaps a hollowed-out log, would be used to frame a specific star or the rising sun, guiding the final adjustments until the stone's edge sliced the sky in perfect agreement with the heavens. This was not guesswork, it was precision engineering with Neolithic tools. The coordination required was immense, involving hundreds of people working in unison, directed by a master builder who held the celestial blueprint in his mind. That a society would dedicate such vast resources, feeding and housing a small army of laborers for decades, speaks volumes. It tells us that aligning stone with star was not a luxury. It was a necessity so vital to their world-view that it justified a civilization's greatest efforts. This profound connection between celestial knowledge and architectural ambition did not just shape single structures, it began to define entire cultures, leaving a permanent mark on their most iconic buildings. These architectural innovations transformed stone and sunlight into a language of cosmic precision. Consider the narrow window of a Mayan observatory, a slit carved with such exactness that it framed the planet Venus for only a few nights each cycle. Or the long, dark corridor of an Egyptian temple, designed so a single beam of light would travel its entire length to illuminate a statue of a god on one specific day of the year. These were not just holes in a wall, they were engineered optical instruments. One of the most elegant examples is found at Fajada Butte in New Mexico. Here, ancient Puebloan artists carved 3 large spiral petroglyphs onto a sheltered rock face. Then, with brilliant foresight, they positioned 2 massive stone slabs directly above them. These slabs act as a natural aperture. For most of the year, light dapples harmlessly around the carvings, but on the summer solstice, a dagger of sunlight appears, slicing perfectly through the center of the largest spiral. On the winter solstice, 2 daggers of light bracket it, and on the equinox, another dagger of light pierces a smaller spiral nearby. This was a calendar, an observatory, and a work of sacred art, all fused into one. The spiral could represent the sun, the cycle of life, or the cosmos itself, with the sun dagger acting as a divine needle stitching the heavens to the earth. This perfect blend of form and function reveals a philosophy where beauty was not separate from utility, but essential to it. A structure that was both useful and awe-inspiring commanded greater respect, ensuring its alignments would be maintained and its meaning preserved for generations. This deep integration of art and science suggests that the keepers of this celestial knowledge were not just technicians, but visionaries. Their role was sacred, and it was a duty that may have been shared by a part of society often overlooked in the historical record. Who were the individuals who spent their nights charting the stars? While we often picture wise old men, evidence points to a more inclusive truth. Women were almost certainly central figures in this ancient science. In many cultures, the cycles of the moon were intimately tied to feminine divinity and the rhythms of human life. It is not a great leap to suppose that women, deeply attuned to these cycles, were among the first and most meticulous lunar observers. The priestesses of the Babylonian moon god Sin, for example, were renowned for their celestial knowledge and their ability to interpret omens. In ancient Egypt, the title astronomer was a role held by priestesses of the goddess Hathor, a deity of the sky and cosmic order. They would have been responsible for the timing of rituals based on the star Sirius, whose annual rising heralded the life-giving Nile flood. These women were not passive bystanders, they were active participants in the great project of mapping the heavens. Their contributions, though often unrecorded in the grand stone inscriptions that favored kings and male priests, were woven into the very fabric of their societies through the oral traditions they maintained and the practical calendars they helped to enforce. Recognizing their role gives us a fuller, richer picture of the human drive to understand the cosmos, a drive that transcended gender and drew upon the unique insights of an entire community. Their legacy, though often whispered in the margins of history, was written in the stars themselves. The names of countless women who charted the heavens have been lost to time, their stories overshadowed by the grand monuments built by kings. Yet the evidence of their vital role is undeniable. In ancient Egypt, priestesses of the goddess Seshat were known as the mistress of the House of Books, overseeing the sacred records that included celestial data. Far later, the legendary Hypatia of Alexandria stood as a towering public intellectual, teaching astronomy and mathematics, her life a testament to the profound knowledge women could possess. Across the ocean in Mesoamerica, the intricate calendar systems that governed every aspect of life were likely not just the domain of male priests. Among the Maya, noble women were often depicted in art holding codices, the very books that contained astronomical tables used to schedule rituals and agricultural cycles. Their involvement made perfect sense. The moon's 28-day cycle has long been associated with feminine divinity and the rhythms of life. Who better to track its phases than those deeply attuned to its symbolic and biological parallels? These women were not mere assistants, they were active participants in the great intellectual project of their time, preserving and applying the celestial knowledge that ensured their communities thrived. Their overlooked contributions remind us that ancient science was a collaborative human endeavor, its story incomplete without acknowledging all of its architects. This celestial knowledge was far too powerful to remain solely in the hands of priests and scholars. It inevitably became a tool for those who sought to rule the earth. The sky was not just a map for priests, but a political tool for kings. A ruler who could predict an eclipse or announce the arrival of the Nile flood was not merely a man, he was a mediator between heaven and earth. This was the ultimate source of legitimacy, a divine mandate written in the stars. To reinforce this power, observatories were often built directly adjacent to royal palaces and state temples, their stark silhouettes against the sky serving as a constant, visible reminder of the king's unique connection to the cosmos. In Babylon, this system was perfected into a state-sponsored science. The king employed a coterie of court astronomers whose sole duty was to watch the night sky for omens. They meticulously recorded everything: the path of a planet through a constellation, the appearance of a comet, the timing of an eclipse. These were not seen as random events, but as messages from the gods about the fate of the king, the success of the harvest, and the outcome of war. If the astronomers predicted a favorable omen, the king could use it to launch a military campaign with the apparent blessing of the gods. If they foresaw disaster, he could perform public rituals to avert divine anger, strengthening his role as the people's protector. The accuracy of these predictions was paramount. It was the very foundation of political stability. An incorrect forecast could undermine the king's authority and plunge the realm into chaos. This direct link between celestial precision and political control fueled an arms race of astronomical investment, driving the construction of ever more sophisticated observatories. But this knowledge of the heavens was too valuable to be hoarded by any single kingdom. It began to travel, carried along the same routes that moved silk, spices, and ideas across the known world. The movement of goods required the movement of knowledge, and astronomy became the ultimate international language. this celestial knowledge became the most valuable cargo never listed on a merchant's manifest. Along the bustling Silk Road between the parcels of silk and spices, traveled something far more enduring, the shared language of the stars. Greek astronomical texts, translated and carried eastward, profoundly influenced Indian scholars who absorbed their geometric models and then refined them with their own precise observations. At the same time, Chinese innovations like the detailed star maps and sophisticated calendar systems traveled west, inspiring astronomers in the Middle East. This was not mere copying, it was creative adaptation. An observatory in Persia might feature a Chinese-style armillary ring for measuring star positions, but be constructed using the sturdy, geometric principles favored by Greek architecture. This cross-pollination of ideas accelerated progress at an incredible rate, as one civilization's unanswered question met another's unique solution. The global network of trade had facilitated a shared, collaborative pursuit of celestial understanding, proving that the drive to comprehend the cosmos was a universal human trait that transcended any single culture. But this grand exchange of knowledge was not confined to royal courts and scholarly institutions. It was integrated into the very fabric of daily existence for ordinary people. The rhythm of life, from the marketplace to the farm, was orchestrated by this celestial clock. A sailor in the Mediterranean did not need to understand the complex geometry of a Greek astrolabe to benefit from it. He simply followed the star charts that guided him safely to port. A farmer in Mesopotamia knew to prepare the fields not because a priest told him, but because he saw the Pleiades cluster rise with the dawn, a signal passed down through generations and reinforced by the community's shared rituals. Celestial events dictated the timing of great festivals that drew people from distant villages, fostering social bonds and a common identity. The sky was a public utility, a vast, open-source database that everyone could access and that connected the most humble daily task to the grand, majestic movements of the universe. This deep integration made astronomy resilient, ensuring its principles were not just stored in stone or parchment, but lived and breathed in the daily life of the entire civilization. A farmer did not need a written almanac to know when to sow his seeds. He simply looked to the sky. The first pre-dawn appearance of the Pleiades star cluster above the eastern horizon signaled the start of the planting season with a reliability that no earthly sign could match. This was not an abstract observation. It was a direct command from the cosmos that synchronized the labor of an entire community. The sun's journey between its solstice extremes was the ultimate calendar, and its key dates were celebrated in festivals that wove astronomy into the very fabric of social life. At the winter solstice, when the sun reached its lowest point, communities would gather to light fires and perform rituals, pleading for its return and the warmth it promised. These were not just parties, they were critical communal acts of faith and solidarity, reinforcing the bonds that held society together through the long, dark months. This cosmic rhythm even shaped the most personal of spaces, the home. In many cultures, the main doorway of a house was oriented to face the rising sun on the equinox, flooding the interior with light on the first day of spring. This was both profoundly practical, welcoming warmth and illumination, and deeply symbolic, aligning daily life with the universal balance of light and dark. From the vast public spectacle of a solstice festival to the intimate, daily sunrise seen from a family's threshold, the celestial cycles provided a shared, living framework for existence. This pervasive influence meant that everyone, from the highest priest to the humblest farmer, was an active participant in an astronomical culture, their lives a continuous dialogue with the heavens. Yet for all we understand about these ancient sky watchers, some of their greatest monuments remain shrouded in mystery. their original purpose lost to time or misinterpreted by later generations. Deep within the Amazon rainforest, massive earthworks arranged in precise geometric patterns lay hidden for centuries beneath the dense canopy. These were not the random mounds of earth they appeared to be from the ground, but a vast, sophisticated network of astronomical observatories, only revealed in their full complexity by modern satellite imagery and LiDAR scanning technology. For generations, the common assumption was that complex societies capable of such large-scale engineering could not have flourished in the Amazon environment. These discoveries, however, have completely overturned that narrative, proving that ancient peoples here possessed an intricate understanding of celestial cycles and encoded them directly into the landscape. They built circular, square, and octagonal enclosures, with avenues and mounds precisely aligned to the solstice sun and other key stars, creating a calendar system on a truly monumental scale. This was a civilization that literally reshaped the Earth to mirror the heavens, and we had no idea they existed until our technology finally caught up to their ingenuity. Similarly, the vast Nazca lines in Peru were long a source of bafflement. From the ground, they are simply shallow grooves in the desert floor, meaningless scratches. But from the air, their true forms as colossal birds, monkeys, and geometric shapes become breathtakingly clear. For decades, theories ranged from alien landing strips to purely religious processional paths. It was only through persistent, on-the-ground archaeological work combined with computerized archaeoastronomy that their true function emerged. Researchers discovered that many of the long, straight lines point directly toward the horizon where the sun, moon, and specific bright stars would rise or set on significant dates throughout the year. The giant spider figure, for instance, is believed to be a representation of the Orion constellation, its legs mirroring the key stars. These were not just artworks, they were a massive, open-air celestial calendar and a sacred landscape designed for ritual observation. The initial misinterpretations of these sites serve as a powerful reminder that our understanding of the ancient world is not fixed. It is a story we are still piecing together, where a single new discovery in a remote jungle or a fresh analysis of a well-known desert can rewrite entire chapters of history. This ongoing exploration is what makes the field so thrilling, a dynamic puzzle where the next piece could be hiding just beneath the sand or the thickest foliage. And in this modern quest for answers, we are turning to powerful new tools that allow us to see through the Earth and across the centuries, rediscovering techniques we thought were lost forever. Our most advanced tools are now peeling back the layers of time, revealing secrets the jungle and desert have guarded for centuries. LiDAR scanning technology, which uses lasers to map the ground surface even through dense forest canopies, has unveiled entire networks of earthworks and structures we never knew existed. In places like the Amazon, what appeared to be random hills are now revealed as geometrically perfect circles and squares, aligned with solstice sunrises. This is not just discovery, it is recovery, bringing lost civilizations and their cosmic blueprints back into the light. Simultaneously, satellites orbiting high above the Earth photograph ancient sites in wavelengths of light invisible to the human eye. Detecting subtle soil and vegetation changes that outline forgotten walls and processional paths. These hidden geometries, once mapped, show us that an observatory was often far more than a single circle of stones. It was the heart of a vast, precisely ordered landscape. Meanwhile, in the digital realm, a new kind of time travel is underway. Archaeoastronomers use sophisticated software to rewind the clock, simulating the precise positions of stars and planets as they appeared thousands of years ago. An alignment that seemed like an educated guess, a doorway facing a certain part of the horizon, can now be verified with mathematical certainty. We can input the exact latitude, longitude, and date of construction for a site like the Mnajdra temples in Malta, and the software will show us that on the equinox, the rising sun's light penetrates a specific oracle hole to strike a central altar, a connection that was theorized but is now confirmed. This marriage of old and new science does more than just verify ancient genius, it deepens our respect for it. We can appreciate their precision without romanticizing their capabilities, understanding the very human process of trial, error, and refinement that led to such perfection. Yet this powerful convergence of technology and archaeology brings with it a profound responsibility. As we identify these sacred sites with ever greater accuracy, we must ask ourselves how to protect them. The very tools that reveal them to researchers can also make them vulnerable to looters and unchecked tourism. Is our primary duty to science to excavate and understand, or to preservation, to leave these delicate alignments undisturbed for future generations? The act of studying a site can sometimes alter its fragile environment, and the knowledge we gain must be balanced with a deep ethical commitment to stewardship. We are not just uncovering the past, we are becoming its guardians. This responsibility to protect these sites raises profound ethical questions. When we study an ancient observatory, we are not merely analyzing stones, we are handling a living heritage, a place that may still hold deep spiritual meaning for descendant communities. For many indigenous peoples, these are not ruins, they are sacred places of worship, directly connected to their ancestors and their cultural identity. An archaeologist moving a single stone to take a measurement could be committing a profound act of desecration, severing a spiritual link that has endured for millennia. The old model of research, where outsiders would arrive, excavate, and remove artifacts, is now rightly seen as a form of academic colonialism. It extracts knowledge while often ignoring or disrespecting the very people for whom that knowledge is most vital. The ethical path forward requires a fundamental shift from extraction to collaboration. This means researchers must approach these sites not as sole experts, but as guests and partners. They engage with tribal elders and community leaders from the very beginning, seeking permission and guidance, and often incorporating traditional oral histories into their scientific interpretations. This partnership enriches the research immeasurably. A local knowledge keeper might explain that a certain stone alignment is not just for the solstice sun, but also marks the beginning of a specific ceremonial cycle, adding a layer of meaning that pure geometry could never reveal. This collaborative model ensures that conservation efforts are culturally sensitive, preserving the site's spiritual integrity alongside its physical structure. By honoring the legacy of the original astronomers through their living descendants, we do more than just protect stones from damage. We safeguard the living culture that gives those stones their true purpose. This respectful fusion of ancient wisdom and modern science offers the most complete picture of our shared human past. And it was this very spirit of building upon past knowledge that set the stage for the next great revolution in our view of the cosmos, a revolution that began not with stone but with glass. The invention of the telescope did not erase the old ways, it simply gave them new eyes. When Galileo first turned his spyglass toward the heavens in the early 1600s, he saw a universe that confirmed and confounded ancient wisdom. He observed the moons of Jupiter, the phases of Venus, and the craters on our own moon, discoveries that shattered the classical model of perfect celestial spheres. Yet his revolutionary work was entirely dependent on the bedrock of knowledge laid down over millennia. The star charts he used, the planetary motions he sought to explain, even the very questions he asked, were all inherited from the naked eye astronomers who came before him. His telescope was a powerful new key, but the lock it opened had been forged by generations of patient sky watchers. This was not a replacement, but an evolution. The meticulous records of the Babylonians, the geometric models of the Greeks, and the solstice alignments of countless stone circles provided the essential map that guided his exploration. Every great leap in science stands upon the foundations of earlier innovation, a continuous chain of human curiosity stretching back to the first person who looked up and wondered. Yet for all their genius, the ancient methods were bound by the fundamental limits of human perception. Their observatories, magnificent as they were, could only measure what the naked eye could see. They could track the slow dance of planets against the starry backdrop, but they could not resolve them as worlds with their own moons and atmospheres. They could predict a lunar eclipse with stunning accuracy, but they had no way of understanding the intricate orbital mechanics that caused it. Their measurements of star positions were phenomenal, yet they remained unaware of the vast distances between those points of light, or that some of those lights were not stars at all, but entire galaxies. The very sky they mapped so perfectly was, in a profound sense, a two-dimensional illusion, a painted dome whose true depth and scale remained hidden. Their legacy is not one of ultimate answers, but of brilliant questions, a testament to how far one can travel using only the mind, the hand, and the unwavering light of the stars. Even with perfect alignments, they could not command the sky. A single overcast night could obscure a critical lunar event, and weeks of fog might block the view of a planet's turning point. Their entire system of knowledge was built upon what the naked eye could see from one fixed location on Earth. They had no concept of the vast continents and oceans that lay beyond their horizon, and thus no way to know that the star patterns they recorded so meticulously looked completely different from the southern hemisphere. This geocentric view, with the Earth as the unmoving center of all things, was an unavoidable limitation of their perspective. They mapped the wanderings of Mars with incredible precision, but they could never know it was another world with ice caps and canyons, because their most powerful tool was their own unaided vision. This meant that faint, distant objects like nebulae or other galaxies were entirely invisible to them, leaving vast portions of the cosmos uncharted and unknown. These were not failures of intellect, but simple boundaries of their reality. What makes their achievements so breathtaking is that they reached the absolute outer limits of what was humanly possible with the technology they had. They extracted every last bit of data from the world they could perceive. This honest acknowledgement of their constraints does not diminish their genius, it refines it. It allows us to see them not as mystics with lost secrets, but as brilliant scientists working at the very frontier of their era's knowledge. Their legacy, however, was far from forgotten. The principles they pioneered of aligning structure with cosmos have echoed through the ages, finding new life in the very heart of our modern cities. The principles of celestial alignment did not vanish with the ancient world. They simply found new forms. Modern architects and designers continue to look to the sky, drawing direct inspiration from the observatories of the past. The Greenwich Royal Observatory in London is a powerful example, its very structure and purpose echoing the ancient fusion of architecture and astronomy. Built to solve the critical problem of navigation by mapping the stars, its design is a testament to function dictating form, much like the solar alignments of Stonehenge or the Mayan Caracol. This is not mere imitation, but a continuation of the same human desire to anchor our buildings to the cosmos. Today, this legacy extends beyond grand public monuments into the very philosophy of sustainable design. Just as ancient builders used the sun's path to passively illuminate sacred chambers, Contemporary architects use sophisticated solar modeling to position windows and overhangs, maximizing natural light and heat while minimizing energy consumption. A modern home might be oriented to capture the low winter sun for warmth, while its eaves block the high summer sun to keep interiors cool, a direct application of the same solar principles understood by ancient astronomers. This enduring influence reveals a profound truth, that the most advanced solutions are often rooted in the most timeless observations. The ancient impulse to live in harmony with celestial cycles has evolved into a blueprint for a sustainable future, proving that their wisdom is more relevant than ever. This deep, symbolic connection between the heavens and human life was not only built in stone, but also woven into the very stories we told each other under the night sky. These celestial stories were far more than simple entertainment. They were the memory palaces of the ancient world. Before the written word could preserve the precise positions of the stars, people wove the night sky into epic tales of gods, heroes, and monsters. The bright scatter of stars we call Orion was not just a random pattern. It was a great hunter, forever pursuing the Pleiades sisters across the heavens, his belt of 3 brilliant stars making him instantly recognizable. This narrative did more than just explain his presence. It served as a perfect mnemonic device, a mental hook that allowed anyone, from a seasoned priest to a young child, to locate and remember a complex star grouping. By attaching a story to the stars, abstract pinpricks of light transformed into a familiar cast of characters, their relationships and adventures mapping directly onto the celestial sphere. This fusion of myth and observation created a powerful, self-perpetuating system. The stories made the science accessible and unforgettable, while the relentless, predictable cycles of the stars gave the myths a foundation in observable reality. The sky was not just a screen for their imaginations, it was a dynamic storybook, its chapters turning with the seasons. This deep interweaving of knowledge and tradition ensured that critical astronomical information, like the seasonal appearance of certain constellations, was passed down faithfully through generations, not as dry data, but as living, breathing epic. Yet the very clarity of this celestial storybook depended entirely on the stage upon which it was read. The same sky could tell a very different story from one landscape to the next, forcing each culture to become a master of its own local environment. The relentless desert sun or a perpetually cloudy coast did not hinder their astronomical pursuits, it defined them. Ancient astronomers were master adapters, and their choice of where to build an observatory was a calculated response to the local climate. In the rain-drenched highlands of northern Europe, builders selected high, open plains where the horizon was clear and sweeping, perfect for tracking the sun's low path in the winter sky. The massive stones of Callanish in Scotland, for example, stand on a windswept ridge, positioned to capture the complicated rising and setting of the moon against a distant, unobstructed skyline. Conversely, in the sun-scorched deserts of Egypt and the Middle East, the challenge was not cloud cover, but the overwhelming, blinding brightness of the day. Here, astronomers turned to the crystal-clear night air, which offered unparalleled views of the stars. Their ziggurats and temples were often oriented with incredible precision to the pole star or other circumpolar stars that never set, objects that could be reliably observed on nearly every night of the year. They learned to read the subtle signs in their own environment, using a specific mountain peak that was only visible on days with exceptional clarity as a marker for a rare celestial event. The landscape itself became a filter, and by understanding its particularities from the prevailing winds to the seasonal fog patterns, they could select the one perfect vantage point where the heavens would reliably reveal their secrets. Their choice of location was a masterclass in environmental engineering. They did not simply build where it was convenient, they sought out the one spot where the sky would speak with the greatest clarity. High in the Andes, Inca astronomers constructed sacred sites like Machu Picchu on mountain ridges piercing the thin, dry air. This altitude offered an unobstructed panorama of the heavens, far above the cloud cover and haze of the valleys, creating a natural observatory with pristine viewing conditions. In the vast emptiness of the Sahara, the same principle applied. The relentless desert sun and cloudless nights provided a perfect, stable stage for tracking the stars. But it was not just about the sky above, it was about the ground below. They adapted their construction to the local climate with brilliant practicality. In rainy regions, they used dense, non-porous stones that would not erode or shift with centuries of downpours, preserving their critical alignments. In windy, exposed locations, they set their monoliths deep into the earth, anchoring them against the elements. This environmental sensitivity was a key to their longevity, ensuring that an observatory built to mark a solstice would still function perfectly 1,000 years later, its stones unmoved and its sightlines true. Their strategic siting reveals a holistic wisdom, a recognition that the earth and sky are partners in the celestial dance. This deep connection to place was then etched into the very shape and symbolism of the structures themselves, transforming cold stone into a language of cosmic belief. The designs of these observatories were rarely arbitrary. A circle of stones was more than a measuring device. It was a model of the cosmos, with the perimeter representing the celestial sphere and the center symbolizing the axis of the world. A spiral petroglyph was not just a solstice marker, it embodied the cyclical nature of time, the endless journey of birth, death, and rebirth seen in the seasons and the stars. The towering ziggurats of Mesopotamia were not just viewing platforms, they were artificial mountains, replicating the primordial mound from which creation sprang, a stairway connecting the human realm to the domain of the gods. Every angle, every corridor, every carved symbol was imbued with meaning. The narrow window that framed Venus was a conduit for its divine influence, and the long temple corridor that channeled the sun's light was a pathway for its life-giving power. The architecture itself was a sacred text written in geometry and alignment, a permanent statement of how a culture saw its place within the universe. This symbolic encoding ensured that the observatory was not just a tool for a few specialists, but a spiritual compass for an entire civilization, its form teaching its people about the order of the heavens every time they looked upon it. Yet the stones themselves often held a deeper numerical secret. The outer circle at Stonehenge was once composed of 30 upright sarsen stones. This number did not arise from mere architectural convenience. It almost perfectly mirrors the 29.5-day cycle of the moon, a fundamental rhythm of timekeeping for countless ancient cultures. This was not an isolated case. In many stone circles across Britain, the number of stones frequently corresponds to key lunar or solar numbers, like 19 for the Metonic cycle, a period after which the moon's phases repeat on the same calendar dates. The very geometry of these spaces was a symbolic universe. The circle represented the eternal, cyclical nature of time and the celestial dome, while the center point was the axis mundi, the still center of the world around which the cosmos turned. Cardinal directions were never arbitrary. An entrance facing the rising sun on the equinox was a declaration of balance and cosmic order, a physical alignment with a moment of perfect equilibrium between day and night. To align a temple with the pole star, which never sets, was to connect it to the concept of eternity and the unwavering seat of divine power. These choices transformed a functioning observatory into a three-dimensional model of a culture's entire belief system. The architecture was a sacred language where every measurement, every orientation, and every number was a word in a profound cosmological statement. But how was this complex, symbolic language passed from one generation to the next? How did a society teach its children to read both the stones and the stars? This knowledge was carefully cultivated in formal schools and apprenticeships, ensuring its survival across the generations. In the groves of Plato's Academy, students did not merely discuss abstract philosophy, they engaged in hands-on observation of the night sky, their theoretical debates grounded in the real movements of planets and stars. This rigorous training blended deep thought with practical skill, forging astronomers who could both contemplate the cosmos and accurately chart its paths. A similar system flourished in ancient India within the Gurukul tradition, where students lived with their teacher, absorbing a curriculum that wove astronomy seamlessly into mathematics, philosophy, and Vedic literature. The celestial rhythms were not a separate subject, but an integral part of understanding the universe's grand design. This immersive education was a sacred trust. A master would pass down not just data, but a methodology, a way of seeing and questioning that honed critical thinking. The student learned to discern subtle patterns, to question an anomaly, and to trust the slow accumulation of evidence over a flash of intuition. This disciplined transmission of knowledge from one trained mind to another was the true engine of their precision. It guaranteed that the complex understanding needed to maintain a stone calendar or predict an eclipse was not lost, but was instead refined and deepened with each new generation. This relentless focus on education and accuracy served one of civilization's most urgent needs: the creation of a reliable calendar that could order the world. The rhythm of the cosmos became the rhythm of daily life, meticulously encoded into powerful calendar systems that governed entire civilizations. The Mayan long count calendar was a masterpiece of celestial mathematics, tracking vast cycles of time with breathtaking precision. It was built upon interlocking cycles of the sun, the moon, and the planet Venus, creating a grand temporal mechanism that could calculate dates thousands of years into the past or future. This was not just for tracking seasons, it was a way to anchor human history within a cosmic framework, predicting the return of gods and the renewal of creation cycles. Simultaneously, along the Nile, the Egyptian civil calendar operated with a different kind of genius. They observed that the annual flooding of their life-giving river coincided with the heliacal rising of the star Sirius, when it first becomes visible just before dawn. They built their entire year around this event, creating a 365-day calendar divided into 12 months of 30 days each, with 5 extra days added for festivals. This solar-based system was so accurate and practical that it formed the bedrock of their agricultural and religious life for millennia, telling priests when to perform rituals and farmers when to sow their fields. The creation of these complex systems required generations of sustained observation and mathematical ingenuity, turning raw celestial data into a functional tool for societal order. These calendars were more than just ways to mark time. They were the ultimate expression of astronomical expertise, proving that the stars could be used to build a stable and predictable world. But the fragile threads of this hard-won knowledge were often vulnerable to the brutal forces of history. When empires clashed and cities fell, the careful work of centuries could be erased in a single, violent moment. Conflict was the great eraser of celestial memory. When the Mongol armies swept across the ancient world, they did not just topple empires, they burned libraries, destroying centuries of astronomical records painstakingly compiled by Persian and Islamic scholars. In the Americas, Spanish conquistadors systematically dismantled the Mayan and Inca civilizations, melting down golden astronomical instruments and burning codices that held the keys to their complex calendar systems. In a single, violent moment, 1,000 years of sky watching could be reduced to ashes. Yet knowledge is a stubborn survivor. Sometimes the conquerors recognized the immense value in what they found. When Islamic scholars absorbed the knowledge of the Persian and Greek worlds they encountered, they did not discard it, they translated it, refined it, and built upon it, creating a new, hybrid astronomical tradition that would later flow back into Europe. This pattern of destruction and preservation reveals a profound truth. The drive to understand the heavens was so deeply embedded in human culture that even the most devastating invasion could not fully extinguish it. Its resilience proves that this was not a mere hobby for elites, but a fundamental pillar of civilization itself, a pillar so vital that it found its way into the most intimate aspects of life, even influencing how people understood their own bodies and health. The same celestial rhythms that guided farmers and kings were also believed to pulse through our very veins, connecting the cosmos to human medicine in ways that shaped ancient healing for millennia. The stars were not just guides for planting crops or navigating seas, they were believed to pulse through the human body itself. Ancient physicians saw a direct, unbreakable link between celestial cycles and human health, timing their most critical treatments by the phases of the moon and the movements of planets. An illness might be thought to wax and wane with the lunar cycle, and the rising of a particular constellation could signal the season for a specific disease to emerge. This was not superstition, but a sophisticated medical framework where the macrocosm of the heavens directly influenced the microcosm of the human form. In ancient Greece, this philosophy was literally set in stone. The famous healing temple of Asclepius at Epidaurus was not randomly oriented. Its sacred buildings and sleeping chambers were carefully aligned with the rising of specific stars, particularly those associated with the healer god Apollo. Patients who came to the temple for dream-based healing would sleep in these chambers, positioned so that the beneficial light and influence of these celestial bodies could wash over them, aiding in their cure. The entire process, from diagnosis to the timing of a surgical procedure, was synchronized with the celestial clock. A physician would consult astronomical charts as diligently as he would examine a patient's symptoms, believing that a treatment administered under a waning moon, for instance, would be more effective for draining an infection. While we now know these direct astrological links are not scientifically valid, the underlying principle reveals a profound holistic worldview. Health was not an isolated event within the body, but a state of harmony between the individual and the entire cosmos. This deep integration of astronomy into medicine shows just how far its influence reached, touching the most intimate and vulnerable aspects of human existence. The legacy of this all-encompassing celestial wisdom did not fade away. It simply transformed, laying the very groundwork for the scientific revolution that would follow. Their patient observations became the bedrock of all modern science. Long before we had formal terms like hypothesis or experiment, ancient astronomers were perfecting the art of empirical inquiry. They observed the heavens, recorded the data meticulously, noticed repeating patterns, and then used those patterns to make testable predictions about future events. This cycle of observation, pattern recognition, and prediction is the very heart of the scientific method. Centuries later, visionaries like Copernicus and Kepler did not start from scratch. They were deeply studying the translated works of these earlier sky watchers, building directly upon millennia of accumulated data. When Kepler puzzled over the orbit of Mars, he was using planetary positions recorded by Tycho Brahe, who in turn relied on observational principles refined since Babylonian times. The leap to a sun-centered solar system was not a sudden burst of genius in a vacuum. It was the logical culmination of a process that began with the first person who marked a star's return on a notched bone. This enduring legacy reveals a continuous thread of curiosity, a human drive to explore that connects the builder of a stone circle to the operator of the James Webb Space Telescope. But what kind of person dedicates a lifetime to such a painstaking pursuit? The true engine of this cosmic understanding was not just the method, but the mindset. It required a rare blend of boundless patience and ferocious curiosity. An ancient astronomer had to be content watching the same patch of sky for decades, knowing that the most critical pattern might not reveal itself within a single human lifespan. This was a profession built on delayed gratification, where the reward for a lifetime of work might simply be a single, minor correction to a calendar, a gift for future generations. Alongside this patience burned an insatiable need to know why. Why does Venus sometimes reverse its course? What force guides the moon through its phases? This relentless questioning, this refusal to accept the sky as a mere mystery, is what transformed simple observation into profound discovery. They were the ultimate puzzle solvers, working on a cosmic scale with the most humble of tools, their greatest instrument being a mind unwilling to stop wondering. Such a life demanded a profound acceptance of delayed reward. An astronomer might dedicate 50 years to watching the moon, only to add a single, minor correction to a complex lunar calendar. His work was not for his own glory, but for the security of his great-grandchildren, ensuring their ceremonies would align with the cosmos for generations to come. This was a science built on selflessness, where the greatest achievement was becoming a single, vital link in an unbroken chain of observers stretching across centuries. Their patience was not passive waiting. It was an active, relentless pursuit of consistency, a willingness to watch the same star rise over the same mountain peak 1,000 times to be absolutely certain of its position. This unwavering attention to detail transformed simple observation into high art. They noticed the faintest star in a constellation, the subtle change in a planet's brightness, the exact moment a shadow's edge touched a specific mark on the ground. Their eyes became calibrated instruments, their minds vast storehouses of comparative data. A single night's observation was a data point, a decade's work was a trend, and a lifetime's dedication was a chapter in a celestial encyclopedia written not on papyrus, but in the collective memory of a culture. This unique combination of virtues, patience married to insatiable curiosity and honed by meticulous attention, is what allowed them to push the naked eye to its absolute physical limit. They achieved a level of precision that seems almost superhuman to us today, not because they had secret knowledge, but because they cultivated a quality of mind that modern life often discourages. Their legacy is not just in the stones they left behind, but in the powerful example of what human focus can accomplish. Even with our most advanced telescopes and satellites, we are still unraveling the mysteries they first noticed. The precise purpose of every stone at Karnak in France or the full meaning of the Nazca spider glyph continue to spark debate and drive new archaeological expeditions. Future discoveries, perhaps from newly scanned jungle sites or reinterpreted clay tablets, promise to deepen our awe for their accomplishments. The story of ancient astronomy is far from finished. It is an ongoing conversation with the past, one that continues to remind us of the timeless power of a patient, curious, and dedicated human gaze fixed upon the stars. Their journey reveals a profound truth about human potential, that our greatest tools have always been curiosity, patience, and a deep connection to the world around us. These astronomers did not see technological limitation as a barrier, but as a challenge to be met with brilliant ingenuity. They transformed simple ropes into precise geometric calculators, entire landscapes into cosmic calendars, and their own collective memory into a living library of celestial data. Their legacy is not merely one of stone circles and star alignments, but a timeless testament to what we can achieve when we observe the world with unwavering attention and a relentless drive to understand. As we peer into the depths of space with our most powerful telescopes, we are continuing the very same quest they began. We are building upon the foundations they laid, stone by patient stone, observation by careful observation. Their story invites us to look up at the night sky with fresh eyes, to see it not just as a void, but as a shared inheritance, a canvas of mysteries that has captivated humanity since the dawn of time. How does this ancient ingenuity reshape your view of science and our place in the cosmos? Let us know what you discovered in the comments below, and thank you for exploring these celestial mysteries.